Hey everyone, I wanted to go ahead and do a little bit of an exam review for you. I know that the exam is tomorrow, but I wanted to work through a handful of practice problems from chapters 8, 9, and 10 in hopes that it will help some of y'all out. And so here we'll begin. I found these practice problems. There are multiple choice problems. These are the sorts of problems that you should expect to see. I found these just by Googling different different topics. For instance, Lewis structure practice problems. And specifically multiple choice practice problems. Anyway, I'm going to begin. This question right here is one that you could see something very similar to, but I don't want you to get distracted. So this question asks you to calculate the formal charge on the nitrogen atom in our molecule CNO-. Okay, what's important for this molecule, what's important for this practice problem is simply the formula Fc, formal charge, sub n, indicating our nitrogen, is equal to the number of valence electrons minus our number of bonds minus our number of non-bonded electrons. Okay, so to solve this, Fc sub n is equal to, well, how many valence electrons does nitrogen bring in? From your periodic table, you'll see that nitrogen is in group number 5, so it brings in 5 valence electrons. So 5 minus, how many bonds does that nitrogen have? Here's a triple bond, here's a single bond, so 4. 5 minus 4. And how many non-bonded electrons does nitrogen have here? Well, it has 0. So our formal charge, our Fc sub n equals, well, 5 minus 4, which is 1. Specifically, though, it's plus 1. So our answer for this question would be C. This here is another formal charge calculation practice problem. You're asked to find the formal charge of bromine, so Fc sub Br is equal to valence electrons that bromine has minus number of bonds minus the number of unshared electrons. Okay, so bromine in group number 7 is going to bring in 7 valence electrons. It's got 3 bonds. 1, 2, 3 bonds. Unshared electrons, it's got 2 unshared electrons. So 7 minus 3 minus 2 is 7 minus 5, basically, so that's 2. And this is a positive number, so plus 2, so our answer there is B. This practice problem, we are actually drawing a molecule, or we're actually selecting from a series of different options to figure out which is the best representation. Now, to solve this problem, what you need to do is you need to figure out how many valence electrons does each of these atoms have. Well, we have OF2, or OF sub 2, so we have one oxygen atom. Oxygen being in group number 6 brings in 6 valence electrons. Well, we have 2 fluorines. So each of these fluorines, since fluorine is in group number 7, it's going to bring in 7. So we are going to say 2 times 7 equals 14 electrons. Okay, so our grand total of electrons from this molecule is 20 electrons. Okay, now this information is all available on the periodic table, so you will need to refer to your periodic table whenever you're drawing a molecule. Now, after we figured out our total number of valence electrons, I'm going to erase all these items here. So we have 20 valence electrons that we can draw. What we need to do is kind of coordinate where those valence electrons are. So I'm going to erase this and rewrite it. We have a total of 20 electrons. Okay, what we need to do is we need to figure out the spatial organization of these 3 atoms. OF2. Well, oxygen, we can go ahead and deduce that oxygen is our central atom due to the fact that it is furthest left on the periodic table. Whenever we do that, we can draw a molecule that looks like this. So at this point in time, this representation right here, there are a total of 4 electrons that have been drawn. After we've drawn our stick figure of our molecule, what we need to do is follow up with placing our remaining electrons. And what we need to do is complete our octet, put 8 electrons around each atom. Right now, what's been drawn here is we have 2, 4, 6, 8, 10, 12, 14, 16. So 16 electrons have been drawn. The octet for fluorine, each fluorine is satisfied. Put 2, 4 around oxygen. We have a total of 20 electrons that have been drawn. 2, 4, 6, 8, starting from the left, 10, 12, 14, 16, 18, 20. So 20 electrons have been drawn. Is this molecule content? Well, based on the fact that we've drawn exactly the number of electrons that we had at our disposal, each atom has a satisfied octet. Yeah, you can go ahead and write this off and say that it's in good shape. Now, does this reflect any of the molecules that we've drawn? Yes, it does. It reflects option D. Okay. Now, if you wanted to take this a step further and figure out something about the formal charges, well, if we figured out the formal charge for fluorine, if we figured it out for the fluorine that's on the left, that's the same as the fluorine that's on the right, due to the fact that they both have a single bond and 3 lone pairs of electrons. Figuring out the formal charge for oxygen. Okay, well, oxygen, there's only one oxygen atom. So our formal charge for fluorine is going to be 7 valence electrons minus, well, our number of bonds, which is 1, minus our unshared electrons, which is going to be 6. So 2, 4, 6. 7 minus 1 minus 6 gives us 0. So we have a formal charge of fluorine, Fc equals 0 for each fluorine. So that's a good sign. We're headed in the right direction. Now for oxygen, well, how many valence electrons does oxygen bring in? Oxygen, being in group number 6, brings in 6 valence electrons. How many bonds does each of these how many bonds does this oxygen see? Well, it sees 2. And how many unshared electrons? 4. So 6 minus 2 minus 4 is effectively 6 minus 6. So that brings us to 0. So we have a molecule in which every single atom has a formal charge of 0. So we're in good shape. So this is obviously not a multiple choice question, but rather it just demonstrates this exercise that you should probably be accustomed to doing. Okay, so we have H2S here. How would you actually draw H2S? Well, first of all, as is the case with anything, in terms of drawing, you need to figure out how many valence electrons are you working with. We have 2 hydrogen atoms here, so this brings in 2 valence electrons. Sulfur, on the other hand, is in group number 6. It's going to bring in 6 valence electrons. So, all told, 2 plus 6 equals 8 valence electrons that we are bringing in for this molecule. Now, in this particular problem, we have our central atom underlined. So both in A and B here, we have our central atoms presented. So what we have is sulfur, H, H. Okay, so sulfur with these 2 hydrogens adjacent to it, that accounts for 2 and 4 total electrons. So the remaining 2 electrons are going to look like that around our central sulfur atom. So this depiction right here shows all 8 electrons that we need to draw. However, is this the most accurate representation of what this molecule looks like? No, more accurate representation would be something like this right here, which if you want to take this into a discussion of chapter number 9, well then this is a pretty good way to do it, because this would be considered a bent molecule. So here is H2S. We have each hydrogen is content with their 2 electrons, and then sulfur is content with 8 electrons surrounding it. Next molecule, CH2Br2. Okay, well, carbon's bringing in 4 electrons. Each hydrogen's bringing in 1 electron, so that's 2 electrons. And then each bromine is bringing in 7 electrons. 7 times 2 equals 14 electrons. So all told, we have 4 plus 2 plus 14, giving us a grand total of 20 electrons. So our central atom is carbon, H, sorry, that's an H even though it kind of looks like a 4. And now that looks like, there we go. Now connect that to a bond. Next up is Br and Br. So 20 total electrons. At this point in time, we have 8 electrons drawn. 2, 4, 6, 2, 4, 6. So each bromine is content because they both have 8 electrons around it. Carbon has 8 electrons through the form of 4 shared single bonds. So this brings us to a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So 20 electrons have been drawn here. Now, have we drawn this molecule properly? Yeah. Chances are, though, what you have in reality is that you've got bromines opposite one another and hydrogens opposite one another because of the size of the respective atoms. But that's the only unique difference to this. So there you go. Again, we're drawing molecules. However, these are polyatomic ions. So we've got ammonium, AMMONIUM, and nitrate. Okay, this is a polyatomic cation and a polyatomic anion. So whenever we see these positive or negative charges, we have to know what to do with that. So the first step in drawing any molecule is to figure out our number of valence electrons. Nitrogen is bringing in 5, and our hydrogens are each bringing in 1, so that brings us to 4 electrons. When you see a positive charge, this seems a little bit counterintuitive, but you got to remember what we're talking about is our charges. So this is actually going to subtract 1. So our total number of valence electrons for ammonium is 5 plus 4 minus 1, 8 electrons. So we have 8 electrons to draw. Which is our central atom? Well, nitrogen is underlined, so N. Adjacent to that nitrogen, we have H, 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 H. Okay, does that look good? 2, 4, 6, 8 electrons for all of our single bonds. Now, we had 8 electrons to draw. We've drawn 8. Well, where does that positive charge come from? Does that positive charge actually land on any specific atom? Well, yes, it does. And we can figure that out by calculating our Fc sub n, or formal charge. Our formal charge is valence electrons minus the number of bonds minus the unshared electrons. Well, nitrogen is bringing in 5 valence electrons minus the number of bonds, which it has 4. How many unshared electrons does nitrogen have in this molecule? 0. So we have positive 1. So if you were asked where does this positive charge actually land, well, it lands on nitrogen. Okay. Now for our nitrate ion, well, the same process. We've got 5 electrons. We have 6 from each oxygen, 18, plus this negative charge here is 1. So that brings us to 23, 24 electrons to draw. Okay, so central atom is nitrogen. Oxygen, oxygen, oxygen. Okay, so this brings us to a grand total of 24 electrons drawn, which is great, that's what we want, but does oxygen have a complete octet? No, it does not. In order for it to have a complete octet, what we'd have to do is put a lone pair there. And if we did that, well, then we've drawn 26 electrons. So what we need to do is basically say that is not right, but rather we need to put nitrogen, double bond to one of the oxygens, oxygen, oxygen, Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this gives us 24 electrons drawn. Is this the right structure? Well, what you can do is you can calculate, we've got basically two different kinds of oxygen here. We've got a double bonded oxygen and single bonded oxygens. Okay, so if we say FC, I'm going to say DB, double bonded oxygen, well, we can calculate that. We could also calculate our FC sub N and our FC SO, or our single bond, SB, single bonded oxygen. Okay, so our formal charge for our double bonded oxygen, we are bringing in 6 valence electrons. That double bonded oxygen has 2 bonds minus unshared electron pairs, or unshared electrons, 4. So 6 minus 2 minus 4 gives us 0. Okay, so this oxygen has an FC equals 0. Okay, now our formal charge for nitrogen. Nitrogen is bringing in 5 valence electrons. How many bonds does it see? 1, 2, 3, 4. 4 bonds. How many unshared electrons does it have? 0. So our formal charge for nitrogen is positive 1. Okay, plus 1. Okay, now our single bonded oxygen, is that the same thing? Well, it's like all other oxygens bringing in 6 valence electrons minus, well, how many bonds does each one of these see? It sees 1. How many unshared electrons? 6. So 6 minus 1 minus 6 is 6 minus 7, so negative 1. So what we have there is an FC negative 1 and an FC of negative 1. So how does this all matter? Well, we have a total of, we want to count up our total number of charges. So this is 0, this is minus 1, this is minus 1, and this is positive 1. So minus 2 plus 1 equals negative 1. So that's where our overall negative 1 charge, as is depicted right there, that's where that actually comes from.